Welcome. My name is Rakshit, and I will be conducting today's session, and then Praveen will be answering any questions in the chat. So if you have any questions, you can either post in the chat or also, since there are only a few people, feel free to unmute and then ask the question too. So that will work since we have a small audience there. Uh, so like Ray mentioned, today's topic is Intel GPU optimization, and the focus topic is memory allocation and memory movement. So we will mainly be learning about various techniques on how to optimize memory allocation and also how to efficiently move the memory between host and device, or device back to host, or device to device, and all those things. Right, so in the agenda today, mainly we will learn how to access the Intel data center Max GPUs on the Intel Developer Cloud, and that's where we will be doing the hands-on work. If you have access to the Aurora cluster, you can also access that and then run that same test code, because we will be accessing all the workshop material from public GitHub, so you can use any cloud. Right? So onto the focus topic, Intel GPU optimization using SYCL. So we will start off by covering unified shared memory versus buffer memory model, and then we will do a deep dive on each one of the memory models, mainly looking at optimizing techniques for buffer memory model and also the optimizing techniques for unified shared memory model. So the main learning objectives of this class today. At the end of this session, you will be able to access the Intel Data Center GPU Max using Intel Developer Cloud. That's one thing. You will understand the buffer memory model versus unified shared memory model. We will look at how to optimize memory copies by using proper accessor permissions and properties. And also we will optimize memory copies by overlapping copies and execution. So these are some of the topics that will be covered today. Right, to start off with, so let's learn about the SYCL memory models. So SYCL offers several choices for managing memory on the device. So one of them, which came out in the earlier specification of SYCL, was the buffer memory model. So mainly a buffer is a container for data that can be accessed from a device and the host. The SYCL runtime mainly manages manages memory by providing APIs for allocating, reading, and writing memory. Right, so that's one of the method. The other method is called the Unified Shared Memory, or USM. So USM allows reading and writing of data with conventional pointers. So you have the choice of explicitly moving the memory, or you can also let the runtime move the memory implicitly. Right. So these are the two memory models at a high level. So let's look at the code directly to compare the buffer memory model versus the unified shared memory model, right? So we will look at the same example code. So this example code is just doing a simple vector increment, right? So if you look at the code here, you can see that we create a queue, and then we have some host memory, which is just a data array. And the host can initialize that data. So this is all just C++ at this point. And then you can see that we create something called a buffer. And then the buffer just encapsulates the data here. And BUF, this is the buffer. And then when we submit the kernel, when we do q.submit, you can see that inside the submission, we create an accessor for the buffer, right? And this accessor is what is actually used to update the content. And you can see that in the actual kernel code, we use the accessor, and the accessor is incremented by 1. Right? And then once the kernel submission is done and it's complete, we use something called a host accessor, which is mainly used to read back the data from device into the host, and then the data becomes available on the host and then can be printed out. So this is a simple example of using buffers. in SYCL. So let's compare this with the unified shared memory model for the exact same example, right? Um, so let's look at the unified shared memory model. So there are two methods. One is implicit movement, and you can see that straight away the code is very small compared to the buffer example that we looked at. So here we use something called malloc_share, which mainly enables accessing the memory on host and device with the same pointer reference, right? And the memory movement happens implicitly. So here you can see that we create uh, a memory allocation using malloc_share. So when you create a data object using this malloc_share, this data can actually be accessed both on the host as well as on the device. Right, so that's what we are doing. You can see that the host can actually access it. We are initializing it to a value of 10. And then in the kernel code, you can see that the exact same pointer reference is used to increment. And then once it is complete, you can again just wait for the completion, and then you can directly access it on the host, right? So the code is very simple when you use the unified shared memory, the implicit movement method. You can see that we don't really have any code that moves the memory here, because all that movement happens implicitly, right? So the compiler knows that we are accessing on the host, so the data is actually kept on the host. And then the moment the compiler sees that the same data object is accessed on the host, then it actually initiates a memory transfer, and then the memory is moved to the device, and then the computation is done. And the same thing happens when it's accessed on the host again. The whole movement, memory copy begins implicitly, and then it's available on the host for printing it out, right? And since these are pointers, we do have to free the data allocation, and that's what we are using this SYCL free function, right? So that is one way of using unified shared memory. And there's also a second method using explicit movement. So this code will be same as the previous code, but except we are doing memory movement explicitly, right? So those are the extra lines of code. You can see that again, in this case, we are doing memory allocation on the device specifically using malloc_device. And then in this case, we do have to add this extra line of code, which will do a mem copy. And this mem copy is mainly copying data from the host into the data_device. And we wait for the copy to be complete. And once the copy is complete, then we actually modify the data on the device. And then once that kernel computation is completed, again, we have to move the data back to the host explicitly. That's what we are doing here. And then the data will be available, right? So the main difference between this code, implicit movement and explicit movement, is that the mem copy, right? So usually we recommend to do the explicit movement because you will have complete control of data movement, and you can actually get better performance by smartly moving the memory at the right time in the code, right? So these are the main various ways to manage memory in SYCL. So since you have the choice of using either buffers or unified shared memory, so what should you be using, right? So, whether you use buffers or USM, all of them are actually doing it's all using the same logic to move the memory. It's using the same driver underneath. So it's all about programmer preference, right? How you want your code to be written, or what kind of coding you're more comfortable with. So mainly SYCL buffers are mainly a new concept, right? It's actually very powerful and elegant because it gives you APIs to allocate memory, read memory, and write memory, and you can set permissions. So you can use buffers if it applies cleanly in your application, as long as it's not disruptive to your development, right? Because it is a new concept, so there is a learning curve. to understand how buffers and accessors work. But if it works out for you, you can use that. Buffers are also very useful in computation that involves 2- and 3-dimensional data representation, right? So if you're writing any of your high performance code using MATLAB, and you're trying to directly convert the logic into SYCL code, using buffers might be a little bit more straightforward, right? Whereas if you look at USM, so this could be very simple for people who have already done C and C++ programming before. So then it will be just a matter of changing a few lines of code, and then you're just creating pointers. So this might be also very useful when porting regular C++ code to SYCL by minimizing changes. So all you have to do is you have to change all your mallocs to malloc_device, and then your code will start running on the GPU device, right? And also within USM, we have shared allocation and also the device allocation. So shared allocation is good when porting code just to get functionality quickly. Like I mentioned, shared allocation is not intended to provide the best performance out of the box. So using explicit movement is recommended because you have complete control over data movement. Right, so the choice is yours, whatever you're comfortable with. But so we usually have examples on both buffers and USM.
Hey, Rakshit.
Yeah.
Just there's a request to comment on malloc device, and also there's a question on performance penalty when using explicit memory allocations compared to the implicit.
So what was the first question? Comment on device?
Malloc device. So there was a request to talk again on malloc device. Yeah.
Okay, so you can see that here in this case, we are doing a new data allocation called data_device equal to SYCL malloc device. So when you say malloc_device, like the function name says, it's doing memory allocation on the device, right? So when we do an allocation like this, it means that data_device allocation is done on the GPU device. And then the size is n, it's integers, right? And that's the reason we are passing the queue, because queue has the information about which device this memory needs to be allocated. Depending if the queue is selecting a GPU, then this malloc_device will be allocating memory on the device specifically, right? So that's why in this case, we have a host allocation, which is a regular array. So we have data, and then we have data_device. And then to do the computation, the first thing we are doing is we have to manually copy the contents of data into data_device. And that's what this statement right here is doing, memcopy, which will copy contents of data into data_device. And we wait until that copy is complete. And once that copy is complete, then we can directly access data_device in the kernel code. So in this case, you cannot access data here, right? If you, instead of data_device, if you try to modify just data, then you'll get an error that the kernel code cannot read data, because data is a regular array, right? So this array is only accessible on the host. That's the reason we have to create a special kind of allocation called malloc_device, and this can be accessed in the kernel code. And then we copy back the data. So in compared with this code, if you look at malloc_shared, so malloc_shared means that this data can be accessed on both host and device, right? So that's one of the reasons we are just updating it on the host, and then we are also updating it on the device, and then it will synchronize and then do all the work for you, right? And coming to the second question, so which is better, implicit movement or explicit movement? So obviously, implicit movement, you don't have control over memory movement or when exactly this data should be moved, because it's all compiler just does it according to its own logic, right? So obviously, since you don't have complete control, you may not get the best performance using implicit movement. So explicit movements, you have complete control when you want to move. You can also write your code more smartly by doing a memory movement while something is happening on the host, right? So you can try to synchronize all the different events, and then you can write your code smartly to get better performance. But in very simple examples, like in this case, it's just doing vector addition or vector increment, right? In this specific example, you may not see much difference whether you use implicit movement or explicit movement, but for larger applications, you can do a lot of different smart tricks to copy the memory, because memory copy is actually an asynchronous operation, right? So you can initiate a memory copy, and while the copy is happening, you can start doing a different computation on the GPU or a different computation on the CPU at the same time. So you have the more flexibility with explicit data movement. Hopefully that answers the question. Please let me know if there's any follow-up. Praveen, any more questions? If not, I'll move on to the next topic.
Yeah, if you have more than one device, implicit movement can figure out which device to use.
Yeah, so when you do the allocation, you're doing the allocation per device, because each queue is associated with one device, right? So if you're doing malloc_shared, it's mainly sharing between host and whatever this queue is set up to do. So if you have multiple queues, then you need multiple implicit allocations, right? You'll have Q1 and Q2. So usually shared allocation is associated with one device. Okay. Okay, I'll move on. Keep the questions coming, and we will answer. I'll pause in between and then find out if there are any questions. Okay. And a quick poll here, and usually we used to have this as a interactive poll. So just in the audience here, so I think we have over 20 people here. So for people who are already doing SYCL programming, if you can just type in the chat window whether you prefer, whether you're using buffer memory model or you're using USM, just type in either buffer or USM, or you can specify both. Just to get an idea, because we did this poll in some of our previous workshops, and then we noticed that I think more than 50% of the people preferred unified shared memory model, and there were about 25% who preferred buffer, and then 25% actually preferred both. So just just to understand about the audience here, what people are using today. Yeah, so I'll just skip over. So I will look at the poll later. Okay, so with that, what I'll do now is we will actually look at actual examples of memory optimization techniques. We'll start off with buffers versus USM, and then we will look at each of these memory models, and then look at some optimization techniques. To start off with that, so I will jump into my browser window now and log into Intel Developer Cloud. Right, so hopefully everybody here in the audience have Intel Developer Cloud account, or any other cloud account which has Intel GPUs in them. So what we will be doing is logging into Intel Developer Cloud, and we will download a repository, and we will access the sample code, which shows some optimizations for memory movement. Okay, so everybody, please go to cloud.intel.com, and if you go to that website, you will arrive at the screen. So if you already have an account, go ahead and then click on sign in. If you don't have an account, click get started, and then it takes only a minute or so. Just create a standard account. You have to enter your first name, last name, email, and then confirm your email, and then you'll have your account. You will be able to log in immediately. So go ahead and then click on sign in if you have an account, or if not, create an account and then click on sign in. So I'll click on sign in, which will log me in, and then this should bring up a console window that looks like this. Right, so I'll give it a few minutes here Let me know if you're facing any issues. We will try to resolve those issues. So this is the steps we will be doing. Go to cloud.intel.com and sign in. And once you sign in, you should arrive at this console.cloud.intel.com, which should have a bunch of options here. I'll let you know what next to do. Okay, so what we did so far is we went to cloud.intel.com, sign in if you already have an account, or if you don't have an account, click on get started and then create an account and then sign in. And then the next step we'll do is we will be launching Jupyter. So if you're in the console page, click on this option that says training and workshops. Right in the console page, click on training and workshops. And once you're in training and workshops, so you have a list of trainings that are available from Intel. So you don't have to go through any one of those trainings. So right up top here, there's a button called Launch Jupyter. So this is the button we will be clicking.
Rakshit, can you please post that README link, the GitHub?
Yeah. So I'll paste the link here, just a link. So if you're catching up, you can just follow the steps in this document here that I pasted in the chat window. So if you're in trainings and workshops, click on Launch Jupyter, right? So once you click on Launch Jupyter, this should open up a new tab. If you have like a pop-up blocker, you might have to disable it, and then it should actually launch a Jupyter Lab interface that looks like this, right? So I'll give it a few seconds here. So please post a question. If you're facing any issues, if you've already launched Jupyter, you can just type in something in the chat window, launched Jupyter or something, so we can get an idea about how many people are successful in logging in. In the meantime, there was a question here, USM explicit. I think this question was from Adrian. Is it more consistent with the most used workflow from other programming models like CUDA and HIP? Exactly. So USM explicit is very similar to what CUDA or HIP uses. Right? CUDA malloc is same as SYCL malloc underscore device. And CUDA memcopy is same as the memcopy that we use, q.memcopy. Okay, so let's see. So we have it launched. Okay, so we have quite a few people who said they are able to launch Jupyter. So once you've launched Jupyter, in the launcher screen, at the very bottom, there is a button called a terminal. So go ahead and then click on this terminal window, and this should actually open up a login prompt. Yeah, don't worry about the training folder because we will be downloading the material using Git clone. So hopefully everybody has launched the terminal window and are seeing a prompt. And what we will do here is we will do a Git clone of this repository. So I will paste the Git clone command in the chat window. Just go ahead and then Git clone. Copy and paste this in the chat in the terminal window. right? So what you can do here is just do git clone. Git clone on the URL, and this should take about 30 seconds maybe. It's a pretty big repository, so it actually downloads the entire one API samples, which includes SYCL, OpenMP, and the rest of it. So that's why it's a big repository. So I'll give it about a minute for everybody to complete the step. So I pasted the git clone command in the chat window. So it's loading. Mine is about 30% now. With these instructions are also in the gist that I pasted earlier, right? Once you launch Jupyter, it tells you to open up a terminal, then you do git clone, right? That's the step we are at right now. So let me show this document again. So I pasted this earlier. So I'm doing this step right here. I opened a terminal. I've already launched Jupyter, and then I've launched the terminal. I just did git clone. And then what I'll do next is I will cd into the directory. So I'll do cd for one API samples. And you can also notice that I just did a git clone in my home directory here. So that's why you see a new folder that is created on the left-hand side. I did cd one API samples, and then I'll do git checkout development branch, right? Just do a git checkout development. And then this should take a few more seconds, and now you're good to go, right? Right, so let's see, any questions? Okay, so that's good. So once you have this folder generated, if you created this in the home directory, it should be available right here where I'm pointing to. So go ahead and then navigate to the folder where the training material is. So if you click on that, you will see a bunch of different folders here inside one API samples. Click on direct programming and click on C++ SYCL, and then click on Jupyter. And then here you'll see all the SYCL training material. And today's session is on GPU optimization using SYCL. So I will click on that. And then once you enter this directory path, you should be seeing these 10 directories here on GPU optimizations. We have different modules here. So today's module will be module 3 here, memory optimization. So if you're wondering how to navigate to this directory, it's also in the gist right here. So we navigated these directories: direct programming, C++, SYCL, Jupyter, right? So hopefully everybody's caught up to here. If you are able to see these different modules, go ahead and then click on 03 memory optimization. And then inside this memory optimization, you will see that there are 3 different notebooks. There's 03 memory optimization, and then there's memory optimization for buffers and also USM. We will start off with the very first one, 03 memory optimization. This, you can just select the default kernel. And you can see that this document has all the details about the explanation I just did with the slides. It gives you an overview of USM versus buffers, what is buffers and what is USM, right? And then we start looking at performance impact of USM and buffers, right? And then let's look at the very first example here. So you'll see that in this first document, we have the simple example for buffers and USM. So this is what we will be, just to get started, we will start running these sample applications. The first one is we'll look at performance impact of buffers. So let's look at the very simple example that we saw in the slides, we have an example for buffers. You can see that we have the host data, a vector for host data, and then we create a buffer for it, and then we have a kernel code, and inside the kernel code we create an accessor, and the accessor is now used to increment the data, and then the initial data is 10, and then once this completes execution you should see the output as 11, right? So how do we run this in Jupyter? So you can see that the code is in this writable cell. So if you hit the play button here, so all this will do is it will just save the file. So you can make any modification to it and then hit the play button, and that will just save the file. And then below that, there is a build and run section. And then we are actually executing a script called run underscore buffers.sh, and this run underscore buffers.sh is available here, and then all it's doing is it's compiling and then also running the binary. So you can click on this cell and then hit the play button, and this should you should see a star symbol right here. This means it's executing. So in a few seconds later you should actually see the output, right? You should see an output like this, right? All it does is it prints out uh, the device name that it's executing the kernel on, and then also the output array, right, which is all 11. If you want to quickly modify the code, you can go ahead and then change this incrementing by 1 to incrementing by 5 as an example, or whatever value you want to do. And before you compile, just go ahead and hit the play button, and this will save the file, and then go ahead and then compile it again. And if you compile it again, the output will be cleared, and then it should compile and then give you the results again. So hopefully everyone is able to follow along and then get this output. So this is just a sanity check to make sure everybody is able to compile and run these examples. So now you can see that the output is changed to 15 because we did 10 plus 5 in the kernel. Let me know if you have any questions.
We're good for now.
Okay, so if there are no questions, so again, there's more documentation. So I covered most of these in the slides, right? It gives you explanation about what the code is actually doing. All right, and you can read through this one. And then we also have 2 more examples, mainly for USM shared allocation, which is implicit data movement. And also there is a code example for USM device allocation, which is explicit data movement. So let's run these examples as well, and then we will go into individual memory models and then work on some optimization techniques, right? So to compile this example again, so I will click on this cell, hit the play button, and then click on the build and run section, hit the play button, and then this should compile and then give me the output. So in this example, you can see that it's using malloc underscore shared, and then all we are doing is submitting the kernel and incrementing by 1. So we get the output as 11. If you've done that, go ahead and then also try out the explicit data movement, right? So you can hit the play button. So you should get the same exact output in all 3 examples. So these 3 examples are good to quickly understand how the memory models work. Right, so you can see that I'm getting the output as 11 in this case as well. Right, so let me know if you have any questions. If not, so this was just trying to get everybody on the dev cloud and to make sure that you're able to compile and run the code. So next, you can close this document, and then we will go into this document 031, which is memory optimization using buffers. And this is where we will be looking at different memory optimization techniques, right? So let's look at the very first optimization technique, which is buffer accessor modes. So mainly, as we learned about buffers and accessors, so accessors have different modes of operation. Mainly, it's accessors can be created with different permissions. So you can either create an accessor as read only or write only, or you can give it a read and write property, right? So based on that, the kernel will function differently, or it can overlap different kernels based on whether there might be any race conditions or not, right? So let's look at a simple example, and then let's try to optimize this code, right? So one of the things we do in all of these memory optimization examples is that we actually measure the clock at the very, we get the clock at the very beginning of the code, and also we then get the clock at the very end of the code, and then try to compute the performance difference, right, between each one of the optimizations that we do. So in this example, what we are doing is we are doing a simple vector addition. As you can see, the main program is right here. So we have three vectors, A, B, and C. A and B are initialized, and C is mainly the output. So what we are trying to do here is C equal to A plus B on the device. So to do this example, we create three buffers for A, B, and C. That's A buff, B buff, and C buff. And then in the kernel code, we are also creating three accessors, right? Which is A, B, and C here. And then the kernel code, all it's doing is C equal to A plus B, right? And then after this is done, then we print out the output C, and then we calculate the duration it took to complete, right? So by default, if you create an accessor like this here, it means that we are giving the accessor both read and write permission, right? So this code is actually same as writing code like this, right? Except that if you don't provide any permissions here, it means that it's actually read write. So that's why we haven't really explicitly given any permissions. So in this case, we have given read write permission, and let's try to run this code as it is, right? We'll save this file by running play, and then we'll click on the play button again, and then this should compile and then give us the result, right? So let's wait a few seconds, and then let's look at what optimization we can do for this code. Right, so you can see that the operation completed. It's mainly telling that C equal to 3, and the compute duration is about 2 seconds, right? So from this code, you can see that the main thing is about access to permissions, right? So we have A, B, and C. All A, B, and C are actually given read-write permission, right? In reality, what we actually need to do is A and B is not actually modified. So we don't really need to give it write permission. And same thing with C, right? C, we are not actually reading it. We are directly writing to it. So this can actually be given just write permission, right? So we can actually write the code so that we can set properties like read only for A and B, because A and B are not modified. And then similarly, C can be made write only, since its value does not need to be overwritten, right? And there's also another property called no initialization, because if we are completely discarding whatever is in C, and then the C is modified with fresh value, then we can set another property called no init, which will also give us better performance, right? So it's mainly asking us to rewrite this the accessor creation by adding some properties. So what we can do is just copy these 3 lines of code. So instead of creating the accessors like this here, we can now create accessors um, by adding these properties, right? So what I'll do is I'll just comment out these 3 lines here, and then I will create accessors with read only, write only, and no in it, right? So let me run this code, and let's wait for the output. So now you can see that we got the output. If you remembered earlier, the previous implementation took 2 seconds to run. So now we have actually reduced by almost half, right? So this computation is actually 1.13 seconds, right? Just by adding these properties as read only and write only for C, we have actually reduced the compute time by almost 100%, right? So why is that, right? So mainly what happens is um, if you say a uh, A is read only, it means that A and B are not actually modified, which means that at the end of this kernel execution, A and B are not actually copied back from device to the host. It's only copied into the device and it's discarded right there, right? Because we are explicitly saying it's read only, it's not going to be modified, which means that the compiler can actually not worry about copying back A and B. Whereas in case of C, we are telling no initialization necessary and it's write only, which means that this C is not even copied into the device. All it's done is it's allocating memory on the device. It's after it's modified, it's just copied back, right? So if we do the allocation as read and write, you will notice that if we do a vtune collection, you will notice that the data is actually copied. A, B, and C are copied into the device. And then at the end of kernel execution, A, B, and C are also copied back. So there's actually 6 different copies that go on. But if we actually write the permissions as read only, and then write only, then only A and B are copied into the device, and then only C is copied back. So there are a total of 3 writes. So that's why we see almost 100% increase in performance, because instead of doing 6 copy operations, this modification will actually do only 3 copies, right? So that's why we see the difference. So if you want to get look at the vtune result, right? So what you can do is just copy and paste this in the terminal. This is the vtune command line, which will capture the vtune, and then you will be able to look at the different outputs, right? So collecting this vtune information might take about 10 to 15 minutes for every example. So this is something that you can do later, after this session, to do complete analysis. But then I have already captured vtune results for these examples. So I'll quickly open vtune and try to find these analysis, and then we can analyze this. Right, so the first example, let's look at vtune analysis when we do without any optimization. I'll just also open the optimized version. Right, so if you capture the vtune with the command line, and then if you copy the vtune data into your local system, you can actually open uh, the analysis for the data collected, and then we can do some analysis here, right? So if you look at this analysis, and then we also have copied the optimized version here. We'll just do a side-by-side comparison. So if you look at the two examples here, you will notice that, in the first example, without any optimization, there is 3 copies, right? So you can see that when I hover over this first one, it says uh, host to device transfer. There are 3 of these here because A is copied, B is copied, C is also copied, right? And then the computation happens here. That is the green section here. And then you can also see again, there is 3 device to host copy. So A is copied back, B is copied back, and also C is also copied back, right? So this is without any optimization. But in reality, we know that A and B does not have to be copied back because it's not really modified. And also this C right here need not be copied into the device because this will get fresh data anyway, right? So if we do the optimization, you will notice that the same code will run faster because you can see that only A and B are copied, and then the computation happens, and then after the computation is done, only C is copied back. So that's why we see only 3 copies as compared to like 6 copies in the first example. Right? So if you want to get these analysis report, then you'll have to run the vtune command that's present there. And this will also give you a lot more information, like what is the total amount of memory that was copied in this example, right? So you can see at the bottom here, without any optimization, about 24 gigabytes of data was moved between host and device. And then after you did the optimization, only 12 gigabytes was moved because there's only 3 copies, right, as compared to 6 copies. So that's the main advantage of setting your read-only and write-only properties, especially when you're using buffers and accessors, right? So I'll pause for a bit. Let me know, Praveen, if there's any questions.
Yeah, this one question, is there a compiler switch to show at compile time which data copies will be performed?
Yeah, I don't think there's a compiler switch. So the only way to find out is, um, using vtune. I think this is a good way to see what copies are being done, because you can actually look up all the different memory copies that happen. Right, you can see what are host to device versus device to host, and then you can clearly see in the graph here, right? And these all tie to, it'll tell you which exact uh, kernel function initiated which copy, and then it'll show you the exact time. So I think this is a good way using vtune to do that. How do you know which exact variable is copied? There's no exact way to find out, but it's depending on your code, right? So your code should actually tell you how many copies is being done. So if you're mainly creating 3 accessors, right, that means there are total 6 possibilities of copies, right? Unless you specify read only or write only, then you can actually eliminate few copies. So this is just doing post analysis. I know what the code is doing. So we have A, B, and C, and that's why we are seeing 3 copies and then 3 copies copy back. So the question is A copied first or B copied first, right? So that's interesting. So let's look at the code, right? So if you look at the code should actually tell us which is performed first. So in this case, right, so these copies happen because since we are doing A, B, and C, I think it's copying one after the other.
I guess unless there is a order queue, or you specify these are asynchronous, right? Actually, this can happen in any order.
Yeah, this can happen, and usually it's, depending on the order we specify it. If we are saying, if you're mentioning to copy A, if you're creating the accessory A first, it's usually triggered first, right? It's dispatched first, and then a few seconds or, a few milliseconds later, the next one starts. But all of these get synchronized before the computation happens, because the synchronization in case of buffers, the compiler will know that A, B, and C are all required to do the computation. So actually there will be a synchronization point here. It will wait until all the three copies are done, and then it's computed. Okay, so um, okay, so let's hopefully people are able to run this, and then people are able to see the performance difference, right? So mainly in your code, you have to go and then go ahead and then make this modification, just add the permissions, and then you might see different performance level, right? And then at the end of each section, we show you how to use vtune, right? If you want to see the graph like I showed, so you do have to install vtune on your local computer. So all this command line is doing on the dev cloud is just collecting all the information. It creates a folder called vtune_data. So you have to zip that folder and then copy it to your local computer. And if you open that, it will show you the graphs like this, right? So I'll move to the next one. So I'll skip the next section, optimizing memory movement between host and device. This was mainly meant for integrated graphics. So I'll skip this section. So I'll go to the next example, which is optimization, which is avoid declaring buffers in the loop, right? So this is a simple optimization. So it's usually overlooked when you're writing code, right? So let's say your code is doing some computation. You have buffers A and B, and then you also have a buffer C, which is used as a scratch or memory to do some computation within a loop, right? So usually uh, when you're discarding the contents of allocation, you can actually move this particular buffer creation outside the loop, right? So keeping it inside the loop will actually recreate the buffer multiple times, right? So which does have some overhead. So this example is just showing the performance hit when you're repeatedly creating a buffer versus when you move the buffer outside the loop and then rewrite the buffer, right? So what we can do is like run the scope as it is. So that's what I'll do. I'll just hit the play button, again, which will compile and execute the code, and it should give you a compute duration. So it did the computation, and then you can see that the compute duration is 0.72 seconds. Right, and the next step, what we can do is we can comment out. Let's copy this buffer creation inside the loop. Let's comment this out, and then we can create the buffer creation outside the for loop. And then let's see what is the performance impact of that. Right, so now you can see that the performance is slightly better, right? It was 0.72. And then if we do this modification, we can see that the compute duration is 0.59, right? So this is a very simple optimization. So it's usually overlooked when you're writing code. Creating buffers does have some overhead, right? Especially if you're creating it within a loop multiple times. So it's always recommended, especially if you don't need the contents of the buffer. If you're just discarding after each calculation, after each loop, then it's okay for you to move that buffer creation once. So the allocation and then freeing of memory is only done once, and you will save some time on the overhead of creating buffers. Right, so hopefully this should be straightforward. Let me know if you're seeing any issues running the code. If not, I'll move to the next example. Right. So the next performance optimization technique in buffers is avoiding moving data back and forth between host and device. Right. So mainly this example will show you different approaches. You can optimize your code so that you don't consistently move your data back and forth. Right. So we have an example here which mainly has a bunch of vectors, right? So it has 6 different vectors, A, B, C, D. There's a sum and the result vector. A, B, C, D are initialized to some value here. And then in the SYCL code, you can see that we are creating buffers for all 6 vectors. And then we are actually doing some computation here. Let's look at the computation steps, right? So we have kernel number 1 here. Which is mainly creating accessors for A and B, and also for sum. And all this is doing is sum equal to A plus B, right? So the first kernel is mainly doing A plus B. And then in the next section, you can see that we're actually creating a host accessor. So we're mainly copying back the result from the first kernel. And then we are doing a simple computation on the CPU. Mainly for all the elements, we are checking whether if the value is greater than 10, then set the value as 1. If not, set it as 0, right? So we are just doing a binary, setting a binary value for the sum. If it's more than 10, it will be 1. If it's less than 10, it will be 0, right? So this computation is done on the host. So in this case, first we are copying A, B, and sum into the device, and then sum is actually copied back to the host, and then sum is overwritten on the host. And then in the second kernel, we are actually copying back the sum. We're copying C and D, and then also we are setting the allocation for result. And then we are doing another computation here where the result equal to sum into C plus D, right? So in this case, you can see that we are actually moving data back and forth, right? So first we are moving some data into the kernel, we're copying back some data into the host, doing some computation, copying back the result back to the device, doing some more computation, and then we are copying back the final result and then printing it out, right? So let's run this code and then see how much time it's actually taking. And then based on that, we will try to do some optimizations. Right, so in a few seconds, it should compile and then give us the result and the timing. Let's wait a few more seconds. Right, so this computation took about 3.4 seconds, right? And it gave us some output here. But as you can see, right, in this computation, one of the optimization we can do is that instead of copying back the sum from device into the host to do the second computation, we can actually leave this data on the device and then do this entire computation by submitting a kernel, right? The third kernel, we already have kernel 1 and 2. We can actually do this entire computation using another kernel submission, right? So that's what this second example does. If you keep scrolling down, you will notice that this has a slight modification. We've introduced a third kernel. Instead of copying back and doing this computation, mainly the computation where we check whether it's greater than 10 and then set it to 0 or 1, we can just leave the data on the device and then just submit to third kernel, right? So that way we are not actually copying back some to the host and then copying it back into the device again. So we will actually save on two copies, memory copies, right? So we can try running this example as well, and this should actually give us a timing of what is the impact of this optimization. So what we've done is instead of doing computation on the host, we just left the data on the device and then submit to the third kernel, right? So let's wait a few seconds here for this to complete, and then let's check the timing. Let me know what you're seeing on your end, right? So it looks like I'm getting some output. You can see that we've actually saved almost half the time, right? So the first example gave us 3.4 seconds, and the second example gave us 1.77 seconds, right? So this is the impact of just saving some memory copies between host and device, right? So we can actually further optimize it, right? So we are submitting 3 different kernels right now. You can actually write the code so that you can combine the computation of these 2 kernels, right? Because the first kernel does not really have any significant dependency on the first kernel, right? So we can actually combine kernel 1 and 2, and that's what the next example is doing here, right? So we are actually doing this entire computation in one kernel, right? First of all, we're calculating the intermediate sum. We create a private variable, do a plus b, and then we are checking whether the private variable, the result is actually greater than 10. If it's greater than 10, then we directly write some value as 1 or 0, right? So we are not writing some accessor 2 times, because the first time we are actually writing it into a private variable, which is just a register, right? And this register value is stored, which is much faster than writing it into global memory. And then we are writing the value sum into global memory only once, right? So we are actually combining 2 kernels into one. So this is one way you can optimize. So this will save on writing one time, right? Because in the previous example, the sum, right, the sum was being written 2 times, right? The kernel number 1 was actually writing it, and then for a second time, it was overwritten, right? So what we've done in this example is that we have created a private variable. We get the intermediate sum there, and then the sum is only written one time, right? The kernel 2 remains the same. So let's run this example, and then let's see what impact this actually made. Right, I have one more optimization, and then we'll open up for questions.
Yeah, we got a question on the previous example. Once we're done with this, we look into that.
Yeah. Yeah, I have one more example, and then we'll jump into questions for a bit. Right, so now you can see that the third example is giving much better performance, right? It was 3.4, it came down to 1.7, and now it's 1.5, right? Because we mainly saved on one write, right? Instead of writing 2 times to the sum accessor, we only writing 1 time. So that's why we see some improvement. In case you're not seeing these performance numbers as I'm seeing, try running it one more time, right? Because note that the way this free version of DevCloud works is that multiple people can be accessing the same system. So 2 people are running the code at the same time. both of you are actually sharing the same GPU. So you might actually see inconsistent performance numbers. But the free version allows multiple users to log in into the same system, same node, and then, but whereas there's also a paid version of the Intel Developer Cloud, where you can actually reserve a system for yourself. So that will get you much better performance numbers. So there might be some inconsistencies between my numbers and your numbers. It could be because at the time I was executing, there was somebody else executing something at the same time, right? So, so I've done three third optimization, and there's also a fourth optimization here. And the fourth optimization, mainly we have two kernels left now, and we are trying to combine these two kernels into one. We are fusing the results into one, right? So we started off with two kernels on one host computation. We changed that to three kernels. We changed it to two kernels, and then now we'll try to do all the computation in one single kernel, right? And that's what this final example is doing. You can see that again, I'm doing creating a private variable t and getting the sum. And then what I do is once I get the one, I check whether it's greater than 10. Instead of just saving 0 or 1 into sum, I'm not even using sum here in this case, right? I'm directly writing the result, which is a plus c plus d, because it's same as c into 1 times plus d, and the other one is c into 0. So that's why we ignored c and then directly doing the computation, right? So I've completely eliminated the need for some accessor, right? So this is one kernel. So let me run this example and see whether we are seeing any improvement, right? So you may not always see when you try to make the kernel complicated, but let's see if we can see result or not. Some people might see some improvement, some may not see, depending on the execution, but let's see. Right, so I'm seeing 1.37 seconds, right? So again, to summarize, we started off, if you look at the four examples, four optimization techniques, at first it was 3.4 seconds, and then we did some optimization. We submitted three kernels, and it became 1.7 seconds. And then we fused two kernels. So three kernels became two kernels, and then we are getting 1.58 seconds. And then finally, if we fuse all three kernels together, we are seeing that we get 1.37 seconds, right? So with each optimization, you can see that mainly what we are doing is we are removing the need for copying between host and device back to the host, and also you're also eliminating creating unnecessary allocations, right? Because we are, instead of doing global memory allocations, we are using just private variables to do internal computation, right? So, and that's and again, in this example too, right? So if you want to see exactly what is happening in the kernel, you can also do the vTune collection for all four examples and then do a complete analysis. So hopefully all of you are able to run these four examples and then see the performance difference. I'll pause here for a bit to take any questions. Probably let me know if there's anything that needs to be
there's
answered.
a comment saying that that the branches are undesirable in GPU kernels where we got the t greater than 10 condition. So any comments on that? I guess we got some branches in the kernels, and that's what I was saying.
Yeah, usually it's undesired. I mean, this is just an example. We are trying to show mainly how to fuse kernels, and then it's just some random computation we chose to show this optimization techniques.
There was another comment saying the third optimization was worse compared to the second.
Just try to run it one more time, right? both your computation, just try to run it one more time. It could be that when you were running that optimization, somebody else was running the same GPU at the same time, right? Because there are multiple people accessing these nodes, and I think it allows 15 people to be on the same node at the same time, right? So if it only takes 2 seconds for these kernels, but at the same time, when you were running, if somebody else was running, you both would be sharing the GPU. You would be using only half the GPU. So that might be some inconsistencies. So I've seen that too. So you just, or you can actually wait until the session is over and then try to rerun this code at a different time when there is no workshop going on, so that you might get a dedicated node for yourself.
Yeah. And one more question. If you go to the first optimization where you are actually initializing the accessor C for every time step, right? Is it first or second? You're initializing the accessor in a loop. I think the loop, yeah, this guy here.
Mm-hmm.
And you're initializing the accessor with the ternary statement. The question is, what if you need to initialize C to 0 at the beginning of each time step?
Yeah, so in that case, you cannot, right? So this is assuming for every loop, uh, you are actually rewriting the data for C. So C is does not require any initialization. That's the only case you can actually move it away from the loop, right? Because even if C had some garbage value, C is actually being overwritten here, right? So we are saying that it's like no init. That means no initialization necessary, and that's why you're able to do it this way. Because C, it's not doing plus equal to, it's just flat out we are writing some new value, right? So it does not require any initialization. That's why we can move it outside the loop. But in case we are trying to update the value of C in every iteration of the loop, then if it requires initialization, you have to move it inside the loop.
And we also
So
mentioned C as no init, right? So
yeah.
yeah,
Uh,
if any other questions, please post it in the chat window, or you can ask directly now before we move on to the next.
yeah. So with that, I think we're at the end of this second chapter, which is buffer optimization. So these are some of the important things to note about buffers. So now I will move to the module 032, which is USM optimizations, right? So we have three techniques here specified. So, right now we have a few optimization techniques. So we plan to consistently update this document if we come across any optimizations that we need to add. So keep up to date with the Git repository. So you might see more optimization. So we have three optimizations we'll be looking at here for USM. So the first one is overlapping data transfer from host to device, right? So let's see what that optimization is. So in this example, right? So some of the GPU devices might have multiple, might allow copying and execution at the same time, right? So in that case, it might be better to, if you have a large chunk of data that you're trying to copy and then compute something on that, it might be a good idea to chunk up the data into multiple chunks and then submit multiple kernels to do different sections of the memory, right? So in that case, you might actually get better performance. So we'll see what I actually mean by that. So let's say so in this case, what we have done here is let's say we have um, Chunk size is defined as this value here. So I think it is, what is that, 10 million? And then there is 10 of these chunks, right? So 10 times 10 million. So it's actually 100 million um, items are being processed here. So instead of processing all 100 million at the same time, what it's doing is we are creating chunks of 10 million items, and then we are doing some computation. So what this will actually do is that um, if you have, let's say, for example, you're doing a computation here. Let me scroll to the section where we have memory allocation, right? So since we have 10 chunks, we have created a for loop here. And for each chunk, we are actually doing device allocation. And then we are filling it with data. So 10 times we do allocations here. And then again, we do use another for loop here. 10 times we actually copy uh, uh, the 10 chunks, and then we do the computation, submit it for computation 10 times, it gets submitted, and then again another 10 times it's copied back. All right. And if you do it this way, since these are all asynchronous, all of these are submitted. And then when the first to do the first computation, this copy will happen, and then the second computation uh, happens, right? And then while this computation is happening, the second chunk can actually be copied, right? So we can mainly overlap the second copy with the first computation, right? And then when the second second computation is done, we have to copy back this data. And while this copy is happening, the second chunk will be doing its computation. So consistently, we can do some overlapping. So that's what we can see. If we do the analysis, you will see that, let's say, we are doing a copy. So this first blue line is actually a copy, right? And then while this copy is happening, the second copy is also initiated, right? Instead of this, if you just had one large memory chunk, right? Instead of this being overlapped, there would have been a big blue bar, right? So instead of that, when we chunk it up, we can overlap a bunch of copies. At the same time, we can also overlap a bunch of computations, which might actually end up performing better in the long run, right? So if you want to test this out, what you can do is like you can run this code as it is. And in the second case, what we'll do is we'll change this number of chunks to 1, and then increase this by one more 0, and then we'll see what's the difference, right? So let me run this example as it is, and then in the second case, what I'll do is I will change the number of chunks to 1, right? So you can see that we're running the code as it is. It's giving me 0.58 seconds. And next, what I can try is I can make it as one chunk, and now increase the chunk size to adding one more 0, and then I can compile and then run it again. Right, you can see that there is a slight improvement in performance, right? It should be the other way around. So I don't know what the first one was. So let's do running it again with 10 chunks. So you should be careful about how many chunks you're doing, right? So if you increase the number of chunks, you're actually increasing the number of kernel submissions. And we also know that the kernel submission time also adds an overhead with every chunk. So it may not be a good idea to have too many kernel submissions. So it should be a trade-off between what is what works out best. So you might have to play with these numbers, start off with one chunk, two chunks, four chunks, and then see at which point you will get better performance, right? So again, I'm seeing like something like 0.58 in this case. So you can change these. You get an idea here about what really is happening when you are doing multiple chunks. You're mainly allowing it to uh, overlap copies, right? So if you did not have this one, you would have one large blue bar, right? So I think I have another graph here somewhere. Way to find this. Yeah, anyway, so I had another graph I wanted to show, but it mainly shows like how chunking up data can actually um, save. Let me see, where is it? Right, so this will give you an idea, right? So let's say you have one chunk, right? So when you do a computation, first you have to copy some data, then you do the compute, and then you do the copy out, right? And let's say we change that into two chunks. When we save it into, divide it into two chunks, you can see that for a small section of copy happens, and then the compute happens, and then the copy out happens. But the second chunk starts copying when the first compute is happening, and then the second compute is happening when the first copy out is happening, and then the second copy out happens, right? So you can see the overall, the amount of copy is the same between the first row and the second row here with two chunks. And you can see that there is a overlap between copy and compute, right? And that's how you can actually reduce the overall time. And the same thing with if you have four chunks, right? If you have four chunks, you can actually overlap more, right? This is how the computation will work, and you can see that can actually reduce the time by almost half, right? So in this graph, I'm not actually adding any overhead for number of kernel submission. So you do, in reality, it'll actually add some overhead for every kernel submission, but you get the idea about what we are trying to do when we do chunk up the data, right? So this is a good way to understand how you can actually improve the performance by chunking up the data. But also, again, remember the second column actually shows you how many kernels are being submitted, right? So the first one is 3 kernels versus 6 kernels, right? So there is actually an overhead. You have to make sure that the performance gained is actually does not you do not lose it by the overhead in the kernel submission. So hopefully this is clear. Let me know if there are any questions. If not, I'll move on to the next section.
Okay, the copy in, compute, copy out can happen at the same time for different chunks.
Right, so we are assuming that this computation in this example is like a vector addition, right? So each chunk can be operated independently because each of the work item is doing its own computation, right? So that's why we are able to do half of the data, submit half of the data in one kernel and half of the data in the second kernel. Hopefully that answers, right? So if you're doing something like reduction, this may not apply to it, but especially if you have a highly parallel computation, something like matrix multiplication or like a vector addition, something similar to that, then each operation is independent. So that's why you can actually overlap. Yeah. Yes, that is correct. I think there was a comment. The hardware also has multiple copy units and supports concurrent kernel execution. Yes, that's right. Okay, so I will move on to this next section, which is avoid copying unnecessary blocks of data, right? So this should be a very simple optimization. So usually, again, this optimization is actually overlooked when you're doing computation. So what I'm doing here in this example is I'm doing a simple reduction example, right? You can see that I'm initializing some data on the host of 1 million items is initialized to some value. I'm allocating some memory on the device. I'm copying the data from host to device using memcopy here. And then I'm submitting a kernel. This kernel is a single task kernel. What I'm doing is a reduction. I'm using a for loop, and then I'm computing the sum of all the elements. And once the sum is computed, I actually save the sum as the first element of the same data array, right? And then what I'm doing is I'm actually copying back the data array and then printing out the sum, right? So this code actually looks, looks like there's nothing wrong with the code. But if you actually look deep into the code, when you're copying back the data, right? Since we are only interested in the very first element here, right? Because that's where the sum is being stored. Because what we are doing is first, we are computing the sum, and then after the sum is computed, the data we have used, is no longer necessary. So we are actually overwriting just the first element with the actual result. So all you need is like the sum value, right? So you don't really have to copy this entire array, right? So this is something very simple that is overlooked, but then if you want to make this faster, you can actually change that to just the first element, right? Instead of copying the entire array, you can just copy back just one item, and that will actually save you some time. And that's what this computation is trying to tell you. So nothing significant, but this is again small things which will make you save a lot of time in copying the data, right? So let's see the result of this one. So this reduction operation took like 4.79 seconds. If I change this, instead of copying all n items, so I just copy the very first element, which is just one element. I should see some performance improvement. It's now we're saying 4.7. So slight improvement. So all we are doing is, since we are copying a billion integers, right, which is almost like 4 gigabytes of data, right? So what's happening is we are copying in 4 gigabytes of data, and initially we were actually copying back 4 gigabytes of data, but instead of copying back 4 gigabytes, we are only copying one element instead of 1 billion elements. So that's what saves us some time, right? So again, it's always good to understand what your code is doing, right? If you don't need to copy back the entire data array, you can just discard and then copy only what's necessary. So that's what the second optimization is doing. So hopefully that is clear. And let's look at this last example, copying memory from host to USM device allocation, right? So mainly, when you're copying data from host to device allocation, there's two ways you can copy. You can just copy from the regular host allocation that is using malloc, right? You can do a copy from malloc to a malloc underscore device, right? Or you can also allocate the initial um, uh, memory on the host using this malloc underscore host, right? So this is a SYCL way of allocating memory on the host. So usually if you copy memory from malloc host to malloc device, it'll be faster than copying memory from malloc to malloc underscore device, right? So let's run this code and understand what this actually means. Right. So mainly it's printing out the two timings, right? So when you are doing copy from malloc to malloc underscore device, we see the time as 0.193. But then if we do malloc host to malloc device copy, it's taking 0.190 seconds, right? So this is mainly because when when the copy happens, malloc underscore host is actually registering the memory. Uh, in the unified shared memory so that the copy happens much faster. But whereas if you're using just malloc, it needs to be registered first, which uses another API, and then the copy is actually initialized. So that's why there's a little bit of overhead when you use a regular malloc. So usually it's a good idea. In previous examples, we were using malloc, right? So especially if you have large amounts of data, it's actually recommended to use malloc underscore host to do your initial allocation. So that way, when you're doing multiple copies, you actually get a significant improvement in performance, right? So this is just the way uh, the compiler does the allocation, right? So malloc underscore host to malloc underscore device will be much faster. So hopefully you're seeing the same results. In case you're seeing slightly different results, try to run the code again, right? So it could be because multiple people are on the same system. Uh, yeah, so hopefully people are able to run this code. So I think I've completed all the examples. So let me know if you have any questions. If not, I will summarize what we have done, and then we can jump into more Q&A. Okay, Praveen, any questions or should I move on?
Yeah, we are good for now. Yeah, let's move on.
Yeah. So that was the hands-on section. So let me just summarize what we learned so far, right? So this is for people who are using buffers. Again, the accessor modes are very important, right, to set in your accessors. That is setting either read-only, write-only, or no initialization properties, right? So this will mainly avoid unnecessary copies of memory between host and device. So we looked at this example where we actually saved 100%. We got, reduced the number of time by half by just setting some accessor modes. Also, this no init property, it's often overlooked, right? So if you don't need to initialize the result accessor, always set no init as the accessor. So that way it does not get copied unnecessarily, right? So that's an important tip. And also avoid declaring buffers in the loop. So we looked at this example. If you don't need to initialize it in every loop, it's better to move the buffer creation outside the loop so that you don't add overhead by creating it multiple times. And also we looked at this example, right? Mainly merging kernels into one. This will avoid copying data back and forth, right? So these are the optimization techniques we looked at. And for USM, we looked at how to chunk the data so that we can overlap copies and then executions of different kernels, right? So this will save a lot of time in your computation. And we also looked at why it's important to use malloc underscore host for allocations on the host and then copy it to the device allocations, which will give you better performance, right? And then finally, we also looked at copy back only sections of data that is modified, right? So in case you're doing some computation and you're only modifying half the array in the kernel, so avoid copying back the entire array, right? So this is a simple optimization, so it's often overlooked. So it might be a good idea to remember this optimization. Right. So that was the training that I had. So there are more resources. So we will be sending out this slide deck. So if you want to learn more about SYCL programming, there's a whole training series on how to get started with SYCL. And then the GPU optimization guide is also online document. There's also a PDF available of all the different optimizations. So be sure to check that out. I will show this again. And then there's also, we have a repository full of sample code, which shows different kinds of SYCL examples. And then there are links to install the compiler and also the specification, right? So let me show you the Intel GPU optimization guide. So if you just Google for Intel GPU optimization guide, you will see the very first link will give you the guide here. So let me change the size of this one. You'll see that you can download a PDF copy of this one. So you'll get the latest version. Just make sure to check the latest version. And you have all the topics here. So the topic we have discussed here will be under general purpose computing on GPU. And you have the entire optimization guide. So today what we looked at is mainly host device memory, buffer and USM, and also host device coordination, right? So there's all the other different optimization techniques also available. So you can read this document, or you can also follow the Jupyter notebooks, right? So we have written this in more training format where you can read documentation and run the code at the same time. But the actual master documentation is actually right here on the web page. So you can go into any one of these sections, and then you will notice that you have the same examples here. So avoid moving data back and forth. So you can read the same documentation. So you have the code here, but you cannot actually run the code here. You have to copy and then paste it, right? So that's why we have written the Jupyter notebook so that you can read the documentation and then check the numbers and then confirm that these optimizations are actually working, right? So this document also has more advanced optimizations when it comes to implicit and explicit scaling and other the matrix engine optimization and also the occupancy calculation and stuff, right? So this you can download this PDF to get a full overview. But I think in future also we might have more trainings focused on specific topics within this optimization guide. So far we have covered 2 topics, which is just 2 out of the 15 different modules, right? So you can also, I think last month we did thread mapping and occupancy, and today we have covered memory optimization. So there are a lot more different optimizations available. So you can go through these one by one and let us know if you have any questions. So with that, so this training is complete. So we'll take any questions you may have.
Yeah, there's a question on buffer abstraction, and is buffer an abstraction that manages a memory in both the host and the device? That's correct. And when do we use buffer and when to use USM? It's a programmer's choice, and both has got its own pros.
Yeah. Right. So, I mean, we've written some guidance, right? So obviously, USM is easy to follow because you already know how pointers work. So it's just a pointer, right? It's a pointer that references memory on the device and the host. So it might be more straightforward if you use USM. And like somebody else commented, the other programming models like CUDA and HIP for NVIDIA and AMD, they also use something which is pointer based, and which might be very familiar. So if you're coming from CUDA development or HIP development, it might be just easier to use USM, right? Because you just have to change the syntax and then you'll be done. But buffers are actually a new concept, right? It's almost made for people who are familiar with API-based programming, who are more familiar with modern programming like Python or something, right? So it's a new concept. There's a little bit of learning curve. So I think one of the advantage what I've seen is mainly when you're using 2 or 3 dimensional data, right? So People who are computer science people usually tend to prefer USM, but if you are coming from molecular dynamics or some other background and you're trying to write code for high performance computing, buffers might be much more easier because you can just copy and paste the code for multi-dimensional data from your MATLAB code into your SYCL code, and it'll just work. Right? But if you're using pointers, it might be a little bit more difficult to understand how the memory layout, how three-dimensional data is represented on a single dimensional memory, right? So, but for people who are coming from computer science background, it might be just simple. Right.
Yeah, and one more advantage is in buffers and accessors, we got data dependencies, and these data dependencies are implicitly handled by the runtime. And in USM, you need to, especially if you're using malloc device, you need to handle that programmatically. So
yeah, exactly, right. So I mean, what Praveen means here is that if you're using USM, right? So you do have to make sure that you add these synchronization steps at every copy, right? Because if you miss one of these weights, right? So then these two executions will overlap and then you might run into data race conditions, right? But whereas in case of if you use buffers, right, a buffer code, all that dependency is automatically handled, right? Because the accessors have read and write permissions, right? If because this accessor, if it's writing some data, if it's read write permission, then the second kernel, if it uses the same accessor, it won't get executed. All the dependency will be handled implicitly. So that's one advantage. I think this is buffer accessors was developed mainly to help people who are coming from different industries, right, who are trying to write up for high performance code, whereas USM is more for computer science people. Okay, so any more questions? I mean, let's see. Okay, does it make sense to install one API on my laptop with NVIDIA GPU or play with the Intel Cloud, right?
yeah, I just answered.
Yeah.
If you want to run your SYCL code on an NVIDIA GPU, you can actually use the CodePlay plugin and run your SYCL code on the NVIDIA GPU.
You
Or
can
if you
do
want to
that.
run,
Yeah. So if you want to run SYCL, all these SYCL code will actually compile and run on NVIDIA as well, right? So, but all you have to do is like install the one API compiler or the toolkit, but you also have to install this CodePlay plugin, right? So just search for one API CodePlay NVIDIA plugin, right? So it's just a small .so file which will enable you to uh, use the Intel compiler to compile for NVIDIA or also AMD GPUs, right? So you can at least test out these code. But if you want to test on the latest Intel processors and GPUs, then you can use Intel Developer Cloud. Also, I think there's a question on, is today's the last installment of this series? Yeah, I mean, for this series, this is the last one. But I think next year we will have more on this same topic. It depends on user interest, right? So if there's any topic on Intel GPU optimization that you are interested, just let Ray know about it, and then we can prepare for more training sessions for next year on any specific topic, right? Because we do have topics that cover other things like shared local memory, there's subgroups, atomics, kernel reduction, there's implicit explicit scaling, and there might be new topics added. So if any of these are interesting for you and you want to need a live session for it, let us know. Then we can come up with another series for next year sometime. But you can also all this training is freely available on GitHub. You can also self-learn it, right? So because it's not just code examples, it also has explanation in the Jupyter notebook, right? So this actually tells you what is shared local memory, and then what are bank conflicts, or using SLM as cache. So there's a lot of explanation here too. But if you want us to come up with a live session, do let us know, and then we can set up something for next year. Okay, so looks like we have no other questions. Trey, we can end this session if you want to wrap up.
There's a question. Can we run the SYCL code on laptops with Intel integrated graphics? I answered yes, we can run the
Yeah.
code on.